The following program is brought to you by Caltech.
Okay, our next speaker is Geoff Blake, who is a professor of planetary science and cosmochemistry here at Caltech. His research expertise is in the chemistry of molecular clouds, and especially the dust and gas-rich circumstellar disks out of which planets form. His technical interests are mainly in high dispersion spectroscopy, including instrumentation development, and he is going to talk to us about the opportunities for airships in planetary science.
Thanks, Lynn. It's great to be here. I'm looking forward to a week of brainstorming with folks in the audience to try and learn about what the opportunities might be. And so, as Lynn said, I'll talk mostly in my part this morning about what the sort of recent discoveries have been in looking at planetary science, especially small bodies in the solar system, and also in the formation of planets and the disks around young stars, and a little bit about exoplanets using two spacecrafts, the Spitzer and Herschel, in the infrared and far-infrared respectively, and ground-based follow-up from Keck, and what some of the opportunities might be. And so again, I'm looking forward to finding out what the capabilities of these airships might be and how we might use them to try and do science we can't do now. Sophia's just getting started, so I will not show results there, but borrow liberally from some of the science case documents for what people are thinking about with science using airborne platforms. Okay, just to remind folks, this planetary science has been around for a long time. It's actually been really interesting, quantitative, hard-nosed numerical conclusions, starting back with Laplace in 1796, where you had the planets known from antiquity. Of course, added lots of knowledge on small bodies. And what he concluded was, right, you knew back then, most of the mass was in the sun, most of the angular momentum was in the planets, right? So that was the major quantitative conclusion back in roughly 1800, was that the mass was all here, angular momentum was here, and he talked about what that meant quantitatively for the way you build planetary systems. We'll come back to in the disks around young stars. It's changed now, of course, almost immediately thereafter, right? This was the popular press of the day, was engravings and things. And so within a couple of years or so, there were beautiful engravings coming out about universal solar systems. So here's ours right here. Here's other various topologies imagined by the artists at that point, only a couple of years after the publication of Laplace's work. We have better rendering tools now that we've all grown up watching. But of course, the really exciting thing is that we can actually study these objects now. So this is the kind of thing I'm not sure if you would do from an airship, but here's a beautiful Keck image of the hot young exoplanets around an A-type star, HR 8799. Scale bar there is 0.5 arc seconds, so linear scale of 20 AU in this case. And then, of course, the beautiful now radial velocity data also from Keck and other telescopes exploring the planets around other mostly sun-like stars, some mass on the vertical axis, distance from the young star on the horizontal axis. Sort of down here, it's empty because of instrumental limitations in the star. You can't measure the velocity accurately enough to look for very low mass objects around stars at long distances. And then, of course, Kepler now pushing well into the sort of couple Earth radius regime, where here's the sort of close-in, so-called hot Jupiters close to the star. Here are probably rockier type planets, or rock and gas envelopes down into the sort of, here's the 0.1 Jupiter radius regime. One thing to think about for me, from airships, for example, I haven't thought much about, but interested in brainstorming some, is if you're not going to sort of get this angular resolution, does the photometric environment from an airship improve so much over ground-based stuff? So, for example, can you move to look at nearby low-mass stars, L&M stars, or brown dwarfs in the nearby neighborhood and do near-infrared, mid-infrared photometry analogs of Kepler, where now you're looking at more of the whole sky, right? You're looking at one little patch of sky here with Kepler. The nearby young dwarfs are spread out over the entire sky. And so there are ways to do all-sky analogs of the optical work that will be done by the next NASA mission, but now for lower mass stars whose emission peaks out in the near infrared. Right? Do airships and small little photometers provide you with a platform for doing very high precision photometry a la Kepler, but not from space, but from these airborne platforms? That'll be fun to think about during the week. Okay? And so the way you connect these two things, and what I'll do in the talk today is talk about both planetary system primitive bodies and, disks around young stars. We don't think you make objects like Jupiter inside the orbit of Mercury. We think you make them further out. And by the interaction of the young planet with the disk around the young star, there's radial forces that make those planets migrate, and you get this resulting orbital distribution by the process of growing the planet from small dust grains and then having it migrate. Right? So you want to understand these disks around young stars as well. And so the thing that will sort of tie together, at least for me, the exoplanets and the planets are that one of the things we're really interested in is, of course, is how do you build a habitable planet? What makes the Earth wet and alive as opposed to Mars or Venus? And how and when did the Earth acquire its volatile inventory? And if you look at the sort of story of planet formation, we'll go through in just a little bit, the reason that things like the delivery of water vapor or water and organic materials to the early Earth and also to these planets as well from these small bodies, things like comets or asteroids, is that if you think about how you build up an object like the Earth, it's hierarchical. And so you have events like this that happen most likely in the history of building the Earth. So it'd be something like a simulation of the Earth-Moon forming impact where you have a proto-Earth, maybe 70-75% of the mass of the Earth being impacted by a roughly Mars-sized impactor. Even before an event like this, the accretional heat of building a planet that's something like a few thousand kilometers in radius, especially if there was live aluminum-26 early in the game, is sufficient to melt the planet. An impact like this also, again, is sufficient by itself to melt the planet, lead to silicates, magma oceans, and so you don't have a primary atmosphere that survives this sort of process. And so one of the ideas is that you build the planet, and then late in the game, right, you deliver via comets or asteroids organic-rich, water-rich material. And so you want to know what the history of these small bodies is, how they move around, how they might be delivered to either terrestrial planets or the satellites of Jovian planets, what their composition is, etc. Okay, so that'll be sort of the motivating theme is how do we learn about water and volatiles in both our solar system and also forming solar systems, and what might airships tell us about those kinds of questions. So of course the way we study these things, we can't go there and sample them, so we use spectrographs to do this. Here's the pretty images from the high-res spectrograph on Keck, all the stellar lines that are used to do the radial velocity. One thing we haven't worried about with these instruments yet, and we should brainstorm a little bit during the week, is that we don't really optimize these things for size and weight on the ground. We optimize them for throughput and image fidelity at the focal plane. So if you sacrifice, for example, some image fidelity at the focal plane, use things like immersion gratings to make your gratings, you can make instruments that are much, much more compact than are typically true on ground-based telescopes. But that's not been explored yet, and it's not been an issue that's been explored by any of the spacecraft, as we'll see in just a minute. Okay? So we use that information, right? We disperse the light at optical wavelengths. We measure the photosphere of the star. I'm a chemist, so here's my version of the astronomer's periodic table, where the size of the symbol is the abundance by mass of the elements. So hydrogen, helium, roughly 99%, 1% of the area in the big box here are all the condensable elements: water, methane, ammonia for the ices, silicates and iron oxides for the refractory dust grains. We know a lot about stars from their photosphere, what they're made of, and the question is for things that are further from the stars, like a forming planet or a disk around a young star, what's the right wavelengths to use? This is where the airship and the satellites come in. Of course, as you move away from the young star, just do the simple blackbody calculation. Temperature goes like 1 over the square root of the distance. So things out at, say, 1 AU, peak here at around 10 microns for the thermal radiation. Things out at 100 AU, peak out here at sort of, hundreds of microns. So things that are close to the star emit in the infrared. Things that are further away from the star or in the midplane of, say, a disk around a young star where it's cold emit in the far infrared or terahertz region. And what are some of the tracers we use to study these things? Okay, and so in the infrared, we're sensitive to the disk surface or to things that are emitting at 300 Kelvin, so things like the Earth or asteroids. Out in the far infrared, where Herschel worked until just a couple days ago, right, we're sensitive to things that are much colder, right, things at a few tens of Kelvin. Let's look at how we use those tracers. So here's sort of the thing that Steve talked about, but now at high dispersion, which will be my focus. Here's a little slice of the infrared for a comet coming in. So we have wavelength on this axis, position in space in a given order. So these are the high-resolution orders of the Echelle, and then separated the orders out with the cross disperser, so high dispersion along here. All these little chunks out of the spectrum are the atmospheric lines from the Earth's atmosphere. It's about 3 microns going out to about 3.8 microns here, and as Steve showed us, right, in the far infrared, it's even worse from the ground. But even from Mauna Kea, right, the important point is here's a blow-up of that little 3 micron region. Now for a disk around a young star, here's emission lines from OH. Here's some HCN emission lines here. Here's the atmosphere. There's actually 2 plots here. You probably can't see them both. So the green is a continuum source with a synthetic model of the Earth's atmosphere. The black are the data. So here's a little spot where right here where the data peaks out above the model, this little OH emission line here. It's only about 1% of the continuum. So you can see most of the structure in that spectrum right here is caused by the absorption of the Earth's atmosphere. And even at high dispersion, these things, as Steve showed us, go all the way down to 0. So here's a water line here. These are methane lines here. So even from Mauna Kea in now, right, we're in the so-called L-band window Steve told us about, right? These lines are optically thick at line center. So if you want to study, right, in your exoplanet or your object, things like methane, oxygen, carbon dioxide, these are the most important species you want to study to understand the atmosphere, for example, of the Jovian planets or exoplanets, right? You have to fight your way through this atmosphere, and you can only do the observations at times when the Doppler shift is large enough to move the features you care about, right, with respect to the atmospheric lines. And one of the huge advantages of going to either SOFIA or the airships, as Steve showed us, is these lines all narrow dramatically. So the Doppler shift you need to get away from the core of the optically thick lines becomes much, much less in the infrared. So you can measure, for example, emission from comets at much smaller velocity offsets than you can typically, right? So for both either low or high resolution spectroscopy, here's low resolution first. So here's some beautiful Spitzer data of the ices around young stars. You can do things like carbon monoxide and the water ice feature at 3 to 5 microns from the ground. You can't do CO2. You can do some ground-based work here around 10 microns, but things that Steve showed us around 5 microns can't really do from the ground from Mauna Kea, but you can do them from, SOFIA or from space. For a planetary science example, here's one that just came out. This is from Kevin Hand and Mike Brown. This is now 3 to 4 microns. So here's the L-band window again. This little notch right here, right? So here's some of the water ice features on. This is for Europa. This is hydrogen peroxide in the surface of the Europa's, in this case is the leading hemisphere. So here's a subtraction from this sort of continuum. So here's the hydrogen peroxide feature right here. Even from the ground with a 10-meter telescope, the radiation environment is severe enough at Europa that these data from the ground are better both in spectral resolution and in spatial resolution than can be acquired currently by the Galileo satellite just because of the radiation environment and the capabilities of that instrument. And so you can look for things like, in this case, that was hydrogen peroxide on the surface. At higher dispersion, you can look for gases. So Io's here in the background. Here's the surface of Europa. You can look for things like SO2 in both the far infrared and the infrared. From Io, you can look for water vapor. We'll see an example of that in a minute, not for Europa, but for Enceladus. And you can also look for features on the surface at lower dispersion. Okay. For comets, when they come in, of course, I'll come back to Enceladus in just a minute. For comets, as they come in, once they begin to evolve gases. You can do two experiments. You can look for the scattered light from the sun. So here, for example, is the dust tail of Hale-Bopp. Here's the ion tail. Here's some beautiful spacecraft flyby images of the nuclei of these comets. So you look either at scattered light from the sun or thermal emission from the comet. We'll do the scattered light first. Okay, so this did not come out very well. I apologize. So we'll move on. But there's sort of there's scattered light emission spectra here of various objects. Here's the data from the telescope. This is Keck again. It's hard to do. What you find, though, and here's the key point for going forward, is that comets are diverse. We've done now only about 15 or so of these from the ground in the infrared. You see large differences in the chemical composition. It's not important what these are. Just notice that the pie charts are different. Right? These are different ices in comets, and they don't look the same. We don't understand why they're not the same. We only have a small sample. We need a much larger sample of comets. And again, we're biased by having to have large enough velocity shifts, right, to be able to see comets. So there's some apparitions where the comet's bright, but the velocity from the Earth shift is small. We can't study things like methane and CO2 through the Earth's atmosphere. And so we don't study those comets because they don't have the right velocity at perihelion. In the far infrared, turns out water, as Steve showed us, water is a much stronger absorber in the far infrared than the infrared. The dipole moment of water is large enough that the water lines are much deeper in the far infrared in the millimeter than they are in the infrared. So most of what we know about water so far has come from the Herschel satellite. Here's one that I was involved in. This is 103 P Hartley 2. It's what's called a short period comet, so it came most likely from the Kuiper belt. Here's H2 18O. Now this is pure rotational lines out at that roughly 550 gigahertz or 600 micron zone that Steve showed us. Here's the emission from singly deuterated water, so HDO. And the thrust of this paper was talking about what, again, the delivery of water might be to the early Earth. So why does deuterium tell you about these things? We'll come back to this plot in just a minute. Here's a little bit of deuterium chemistry because it ties into the Sophia science case and some other tracers. So the basic idea is the deuterium atoms all come from the Big Bang. Stars eat deuterium. So when you make molecular hydrogen in molecular clouds or the disks around young stars, most of the deuterium is carried in the HD molecule. But when you measure the energies of chemical reactions, you do so from what's called the vibrational zero point level. So if you have H plus H to make a molecular hydrogen chemical bond, there's a 0 point energy that's half the vibrational frequency of the molecule. So the 0 point energy for H and H is larger than the 0 point energy for H with deuterium or two deuterium atoms just because of the mass of the deuterium atoms. So that difference in the 0 point energy leads to differences in the overall reaction energetics. So this reaction, HD plus H3 plus, you see this in the aurorae of Jupiter, for example, going to H2 and H2D plus is actually downhill. So it's downhill by about equivalent energy of 230 Kelvin. So once the temperature gets below 230 Kelvin, you drive this reaction to the right towards H2D plus. And then it's shown in this nice slide from Roald Stark about the great instrument. When you drive deuterium into this H2D plus molecule, it can transfer a proton to other molecules like water or ammonia, and so you enhance the deuterium content of water or ammonia at low temperatures. So this happens only when the temperature becomes low enough to drive this chemical reaction toward the products. Okay? And so at low enough temperature, right, you can get huge enhancements over the cosmic value of deuterium, but only in compounds like water or whatnot that are low in abundance. So here, coming back to the comets, the basic story is here's what we think the protosolar value is, about 2 by 10 to the minus 5. So about HD over H2 is 2 by 10 to the minus 5. Here's the Earth's oceans here in blue. It's called standard mean ocean water. So it's enhanced by about a factor of 10 over the protosolar value, cosmic value. So we have the water in the Earth's oceans is enriched in deuterium, so had to have seen at some point low temperature. Don't know when that happened, but at some point there was low temperature in the water around the early sun. And so The Earth's oceans are here. Previous measurements of comets were up here. So these are all what are called long period or Oort cloud comets. So Halley was from the Giotto spacecraft encounter. Hyakutake and Hale-Bopp were from ground-based observations. And then here's our measurement. The surprise in our measurement with Herschel was that this now different reservoir of comets, this short period comet reservoir that comes from the Kuiper belt, where the naive expectation was you make those further from the sun, they should be formed in a colder environment, they should have larger D to H ratios than the short period comets do, which come from the sort of Saturn to Uranus zone. But lo and behold, this one comet had values that were consistent with the Earth's oceans. We've done a couple more. We're done now with the helium's gone. So there's one more short period comet that has an upper limit that's right about here. So not detected the HDO, but it's consistent with the Hartley 2 result. And two other long period comets that basically put D to H values somewhere in this sort of range of the previous detections. So we have this conundrum now. We have one or two measurements with Herschel. That's it. Of the short period comets, a few now of the long period comets. And there seems to be this dichotomy that exists between those two that we won't answer what's going on unless we have more samples, or we need more measurements of this type. And you can see for this comet, just to come back, what I'll do is I'll update the talk and I'll put these numbers into units that we can all think about. But these were long integrations, right? This was the bulk of the US time for comets. It's about 10 millikelvin or so on the scale. I'll put it in the Jansky's watts per square meter. But this was something like, 6 hours of integration time with Herschel. So a lot of integration time on a fairly productive comet.
Is this possible?
Go ahead.
With
Well, it depends entirely then on the production rate. So this was a comet that had, go back here, sorry. This was not a particularly spectacular comet, right? So this production rates of about 10 to the 27th. So for things like this, you would need with a heterodyne instrument on Sophia, you would need about 10 hours of integration time to do this. But for a more productive comet like Hyakutake or Hale-Bopp, you could do it in 20 or 30 minutes. So it depends entirely on the apparition in the comet. Again, just reminding us about the fact that Herschel works at long wavelengths. Here's Enceladus. The advantage of going to longer wavelengths is you don't have to do the reflected light from the sun, so you can do things at larger distances. Here's the Herschel measurements of the water torus around Saturn induced by Enceladus. So the geometry between Swass in 1999 and Herschel in 2009, right? So we went close to the ring plane. So there's this torus that exists around Saturn. That's a water torus from Enceladus. What you're seeing here is the absorption against the continuum of Saturn with the Herschel, because we're right on the torus is right here. Earlier with Swass, right, the torus was kind of more diffuse around here. You don't see that nice strong absorption from the torus. You can map this out with Herschel and see this tenuous atmosphere torus around Saturn, which is responsible for the formation of the E-ring, for example. Watch its dynamics. If you had a platform that could measure water vapor over long periods of times as the seasons change at Saturn, right? So that's a case where you want long baselines, longer baselines than spacecraft will give you to make measurements of things that change with time in the solar system. Okay, other things you can do in the far infrared. Here's some other tracers again from the Sophia science case. Here's one we'll come back to in just a minute. So here's H2. So remember that was that H2D plus was what did the proton transfer. So in either the ISM or in disks around young stars, you might want to try and detect that ion. The ground state transition is at about 1.4 terahertz. So that's up at about 260 microns or so. It's not doable from the ground. This ground state ortho transitions, there's two flavors, just like for water. But unlike for water, collisions of H2 with H2D plus can exchange the spin states. And so even though this state has a different nuclear spin than the ground state, it can relax via collisions in the ISM or in disks. And so this is a metastable level here that relaxes fairly quickly. So even though there's this transition out here at 372 gigahertz, it's available, for example, to ALMA. The expectations are that in cold gas, where you drive most of the deuterium into this ion, is that relaxes. You're up here at about 80 Kelvin, and so the predictions are that this line should be very, very weak in cold, dense gas, where the H2D plus is is most abundant. You can also drive yourself all the way to D3+, right? So the same reactions keep going. So H2D+ will react with HD to make D2H+, and D2H+ will react with HD to make D3+. So you can see things like, for example, doubly deuterated water and triply deuterated ammonia that are 12 or 13 orders of magnitude more abundant than you expect because you drive this deuterium content all the way to things like D3+. That ground state transition is around 1.5 terahertz, or about 200 microns or so. And the other really important one is HD. It's about 112 microns or so. It's 2.7-ish terahertz that the GREAT instrument is targeting. It's in a nice spot for the atmosphere at sort of low velocity shifts, sort of following along with Steve says, but there's trouble lurking both to the blue and to the red if you try and Doppler shift to look at the HD. I'll just zip through this real quick. It's just basically about how you make a planet, so folks want to look at that, they're welcome to. For the disks around young stars, how might the airships compete? You're not going to spatially resolve things the way ALMA can. Here's some beautiful early images from ALMA of a disk around the nearest star, TW Hydra, but you will do things that ALMA can't do. So here's a detection of water vapor from the TW Hydra disk in the lowest ground state lines. Again with Herschel, same kind of thing, right? The main beam temperature here is about 20 millikelvin, 2025. So this was not quite the 10 hours of integration, but it was 4 or 5 hours of integration time with Herschel. This is the nearest disk to us around young stars. So things that are at Taurus, for example, or Chameleon will take about a factor of 10 longer integration time. So we need either a bigger telescope, this is a 3.5 meter telescope, or better detectors, and that's going to be hard to do. But what's nice about these lines is that we measure now the water vapor content in the colder outer part of the disk. So by combining these data, for example, with data in the infrared part of the spectrum, we can measure where the snow line in the disk is. So we can measure where the water vapor goes from vapor to ice, and we can measure the amount of vapor in the outer disk and the inner disk and tell about the time scale for transport of icy solids in the young nebula, the disk around the young star. And again, we do that by just combining high dispersion data in the infrared. So here's some CO emission lines with Keck. Here's the beautiful forest. So we saw a forest of emission lines in the far infrared from Steve, the HEXO survey. Here's the photosphere of a young star, done by Joan Legita and John Carr. These are almost all water vapor emission lines, but if you zoom in, there's water vapor here. Here's hydrogen cyanide. Here's acetylene. Here's carbon dioxide. All those things we care about, for example, in the atmospheres of exoplanets as well, right? And so thundering emission from all these things, not velocity resolved. So in the Keck data, just to go back real quick, right, we can velocity resolve these lines and tell you how far from the young star the gas is. If it's orbiting in Keplerian rotation, for these pretty Spitzer data, right, we measure the total intensity of the lines, but no line shapes. We have no idea just from the Spitzer data, apart from the temperature of the gas, where this gas is located. So we follow that up. This is call it Salik's work for a thesis. We follow that up. There's hundreds of detections now from Spitzer. We follow that up in a few cases from the ground with Keck. So here are velocity resolved emission lines now from OH and from water around 2 young stars at the sort of few tens of kilometers per second. So these line shapes tell us where the water vapor is around the young star. And we can only do hot stuff. Right? This is from the ground at 3 microns. These big gaps here because even from Mauna Kea, things that are only excited by a few hundred Kelvin are optically thick in the Earth's atmosphere. You can't get enough velocity shift to measure them. From Sophia or from an airship, you could work much closer to the line center and actually measure the warm, not the really hot water, and actually map out what the snow line looked like. Right? You could actually map out where the vapor turns to ice by resolving these line shapes as a function of energy and measuring the kinematic patterns. And so what Sophia or airships would do would let us make these measurements over much wider energy ranges and for larger numbers of samples. We have hundreds of disks that we see with Spitzer, but only a little handful that have 3 micron measurements with Keck. and where things are going in the sort of future, right? So we fight to do these things from the ground. We've learned how to subtract the Earth's atmosphere pretty well. The dynamic range here is about 3,000 or 4,000 for these bright stars. So one of the things that we're trying to do, and might be even better from an airship, at least for bright stars, is to directly detect exoplanets not in transit by using the Doppler shift of the planet, and just taking an idea from astronomy where you measure spectroscopic binaries that have different spectra by doing spectroscopy and Doppler tracking the companions. So here, for example, in a stellar case, it's the primary of the bright star. You see in these bright lines here. Here's the secondary, the lower mass companion that has a different spectrum than the primary. And so if you believe you have enough noise, you can try and do this for exoplanets around stars. And again, it's the same actors. If you look at models of these hot Jupiters, the things you want to look for are water vapor, methane, CO2. So the same actors that live in the Earth's atmosphere, you have to try and fight your way through. Here's, for example, one case. This is Rho Cancri E. Here's the star. This is now 3 micron data from Keck. So we go out where the planet is sort of maximum contrast against the star. It's still only about a part in 10 to the 4th or thereabouts. So here's the stellar velocity, very easy to see. Here's on one night the planetary radial velocity, and there's a couple papers from CRIRES now using CO. Here's our data for water vapor, we think, in the atmosphere around Rho Cancri. This, of course, is best done from space, but from an airship platform where, again, you can work. The velocity shifts here you can see are, for example, for these, this is an 8 Earth mass planet around a K-type star. The velocity shifts are hundreds of kilometers per second for the planet, so you're well removed from those Doppler cores of the lines, right? You're at velocities where from Sophia or from an airborne platform, you're well removed from the cores and the lines, and you can try and detect the planet in this case with fairly high fidelity. Yeah, Paul?
So, does the nature of what we're looking at plus the star tell you what kind of distance and period you have to be?
Yeah, so here you know these are ones where we already have the radial velocity of the star from optical measurements. So what the idea here is by measuring the radial velocity of the star and the planet, you break the M sin I degeneracy. And if you know what the mass of the star is, you know what the mass of the planet is. And you're just asking the question, what's the velocity of the planet that's consistent with that radial velocity solution? So these are objects where we already know what the radial velocities of the stars are from the optical surveys. But we don't know what the inclination angle of the system is, right? So by measuring the velocity of the planet along with the star, then if you know the mass of the star, from a spectral type, you measure the inclination angle of the system in this case. Long term, if you believe these fits, right? These are cross correlations of the near-spec data with a template model atmosphere like that. If you believe that you're robustly detecting the planet, the goodness of fit of this cross correlation tells you about the composition of the atmosphere. So it'd be a way to try and do composition of exoplanet atmosphere without having to have transiting planets, again, for bright nearby exoplanet systems. And the last thing, just to wrap up here, back to HD. If you look at the sort of one of the critical things about the disks around young stars is how massive they are. We typically right now use the dust around the young stars, a measure of the gas, by measuring the dust emissivity and assuming a gas-to-dust ratio from that gas of solar composition I showed you before. And if you do that, here's the histogram you get for the Taurus star-forming region. So you go from sort of a few hundredths of a solar mass down to a few thousandths of solar mass for disks around young stars in Taurus. And one of the questions is, how much of this distribution is due to uncertainties in the properties of the dust or the gas-to-dust ratio? And so with Herschel again, and for one disk, this TW Hydra disk again, right, here were 2 models that were consistent with the available dust and line data from carbon monoxide. And you can see they differ by almost an order of magnitude in estimated gas mass around this disk from using lines like CO, which become optically thick very high in the disk atmosphere. So again, using Herschel, we tried to make a measurement of HD. At 20 Kelvin, right, the HD I told you is only about a part in 10 to the 5th of the abundance of H2. but it turns out it has a small dipole moment and a smaller line spacing. So HD is about 1,000,000 times more emissive than H2 is at 20 Kelvin. So between 20 and 40 Kelvin, HD becomes a better tracer of the gas mass than H2 or CO does. Here's the detection of the ground state transition of HD towards CB100. It's about 2 hours of integration time with the PAX instrument on Herschel. Here's a non-detection of the 2-to-1 line, which only tells you the gas is colder than about 60 Kelvin. Some other CO and OH lines. So that detection actually lets you go through and then estimate a mass of the disk given the mass of the star, and it's up here at this high mass end. So it's consistent with this solution here, not with this solution here. And so again, this is now one detection. So we have this detection just showed up in Nature this year. There are 2 more detections sort of in the queue that Herschel has done, but that's it, right? And so here the flux is about a few by 10 to the 8-18 watts per root hertz. This line is totally unresolved again with the PAX instrument on Herschel, which is about resolution of a couple thousand. So this line to continuum ratio, it's only about less than 10% here. It's probably about 1-to-1 or even 1.5-to-1 in a heterodyne instrument. So the GREAT instrument will be targeting this tracer to try and make high kinematic resolution observations of HD. Again, small number statistics. If you have enough integration time and a big enough telescope, you can think about doing tens of objects if you have 5 to 10 hours of integration time available on a sort of 2 to 3 meter class telescope at 50 or 60,000 feet. So with that, I will close and take any questions you have.